Let's look at some AP practice questions that are related to limits. Here on question number 6, we're asked to find the vertical asymptotes of f of x, which is a rational function. Whenever you're looking for the vertical asymptotes of a function, the first thing we should do is determine what values of x make our denominator equal to 0. And in order to do that, I need to factor this function. And while I'm factoring, I'm going to go ahead and factor the numerator and the denominator. So in my numerator, I've got 2 times x squared minus 1, and x squared minus 1, of course, factors into x plus 1 and x minus 1. Then in the denominator, x squared plus x minus 2, well, that's going to be x and x. To get 2, we multiply 1 times 2. And to get that positive x in the middle, I need a positive 2 and a negative 1. So here's the factored form of my rational function. Now notice what we have here. I've got an x minus 1 in the numerator and the denominator. And so, of course, those factors can cancel out. Now let's remember what that means when a factor cancels out. First of all, this function f of x is going to be undefined. F of x is undefined at x equals 1, because that's what makes x minus 1 equal to 0, which would make our denominator 0. It's also undefined at negative 2, because that's what makes this other factor 0. But since my x minus 1 factor canceled out, that's an indication to us that we have removable discontinuity at the point x equals 1. It's not a vertical asymptote, it's removable discontinuity. I have a limit at x minus 1. On the graph, we would just have a little hole. Since x plus 2 did not cancel out, then at x equals negative 2, that's where we're going to have the vertical asymptote. And so our correct answer here is answer B. Let's look at this next question. We're asked to evaluate the limit as x approaches 0 of sine squared x over 1 minus cosine x. Now remember, whenever you're asked to evaluate a limit where x is approaching a number, first thing you should always do is plug that number in. So this would be equal to sine of 0 squared. I like to write squared trig functions like this because I think it's a little less likely we're going to make a mathematical error. And then on the denominator, 1 minus cosine of 0. So now we need to know our unit circle. The sine of 0 is 0. And on the bottom, I have 1 minus cosine of 0. Cosine of 0 is, of course, 1. And so with all of that, when I simplify everything, I end up with 0 over 0. So I don't have a limit yet, but when I get 0 over 0, remember that indicates that most likely there is a limit. We need to go back and simplify our original function, change it somehow, so that we can determine what that limit is. So if I go back and look at my original function, sine squared x over 1 minus cosine x, kind of hard to see what I could do to simplify, but one thing I can do with trig functions, we should always look for identities, that maybe we could substitute an identity and change the way this looks. And so in place of sine squared, there's the Pythagorean identity that says sine squared plus cosine squared equals 1. And if I solve that for sine squared, then I end up with 1 minus cosine squared x. And then my denominator, I'm just going to leave that as 1 minus cosine x. So now it looks like I'm getting somewhere. I can't really cancel anything out yet, but if you look at the numerator here, we've got 1 minus cosine squared, and that is a difference of 2 squares. And so the limit as x approaches 0. I'm going to factor my numerator. And it's going to be 1 and 1 cosine x. Sorry, my stylus isn't working there. And cosine x, and then of course plus minus, because that's how we factor difference of 2 squares. 1 plus cosine x, 1 minus cosine x. And then in my denominator, I still have 1 minus cosine x. Well, now I've got 1 minus cosine x in the numerator and the denominator. Those can cancel out. And now I do have a simplified version of my original function. And so once I've canceled something out, then we should substitute the number in again. So if I substitute 0 into what we have left, 1 plus cosine of 0, 1 plus 1, the cosine of 0 is 1, and 1 plus 1 is 2. And so the correct answer here for number 7 is answer C, 2. In this next question, we're asked to evaluate a limit as x goes to infinity. So this time x is not approaching a number, it's approaching infinity. And when we see that x approaching infinity, we need to be thinking horizontal asymptotes. If I have a limit as x goes to infinity, my function has horizontal asymptotes. Now you could use your pre-cal method for determining horizontal asymptotes. I'm going to rewrite this using the method that we talked about in class. Limit as x goes to infinity, and I'm going to divide everything in this fraction by the highest powered term of x in the denominator. So if I look at my denominator, my highest x term, highest powered x term is x to the 4th. So I'm going to divide every term by x to the 4th. So I get 4x to the 4th over x to the 4th minus 3x over x to the 4th plus 2 over x to the 4th. And then in the denominator, 3x to the 4th over x to the 4th plus x squared over x to the 4th minus 1 over x to the 4th. And now let's simplify. So I've got 4x to the 4th over x to the 4th. Those x to the 4ths can cancel out. 3x over x to the 4th, that x is going to cancel out and it's going to turn that 4th into a cubed. Let me see if I can make that look more like a 3. And then 2 over x to the 4th, I can't do anything with that. In my denominator, 3x to the 4th over x to the 4th, those x to the 4ths cancel out. X squared over x to the 4th, that can reduce to 1 over x squared. And then 1 over x to the 4th does not reduce. So just to help us keep this clear here, I'm going to rewrite what we have left. So now in the numerator, I'm left with 4 minus 3 over x to the 3rd plus 2 over x to the 4th over 3 plus 1 over x squared minus 1 over x to the 4th. So now if I look at these terms, and remember, I'm still considering that x is going to infinity. Well, if I consider 2 over x to the 4th, if x is going to infinity, that means my denominator is infinitely large, and so that fraction is getting infinitely small, infinitely close to 0. This is going to 0. Same thing is happening with 3 over x to the 3rd. The denominator is getting infinitely large, so the fraction is getting infinitely small. Same thing down here. All of those fractions are going to 0, and so you can see what I'm left with here is 4/3. And so my limit is 4/3. My answer is C, 4/3. Last question today, or for this video, limit as x goes to negative infinity of this function that involves these exponential terms. Remember that with an exponential function, one end approaches 0 and the other end approaches infinity. The ends of the exponential function don't do the same thing. And so when we're trying to find a limit at infinity with a function that involves exponentials, we really need to think about what each of those exponentials is doing. So I'm going to start with 2e to the 2x, and also let's consider 4e to the 2x, because those two graphs are basically going to be similar. The 4e to the 2x, we've got a vertical stretch, but as far as the end behavior, they're going to be the same. They're both going to either, the ends are going to be going to 0 or going to infinity, and the vertical stretch isn't going to change that. So let's think about what these graphs are going to look like. If I do e to the 2x, I'm thinking about my parent function, and I know what the parent function looks like. If I multiply that x value by 2, I'm just getting a vertical compression. I'm sorry, not a vertical compression, a horizontal compression. But even with that, my ends are the same. And then if I multiply by 2, or in the other case by 4, I'm stretching the graph, but my end behavior is still the same. The end behavior of this graph is still going to look like this. As x is out here at negative infinity, the graph is going to be going to 0. And that's the part we're interested in. Remember, our original limit asked for x at negative infinity. And so 2e to the x, that is going to become 0. And 4e to the 2x is also going to become 0. As x goes to negative infinity, both of those terms are going to approach 0. Now let's think about negative e to the negative x and 3e to the negative x. So I'm just going to start out with e to the negative x, and let's think about what that graph looks like. You can imagine the parent function e to the x, and notice that I'm making the x negative. That's a horizontal transformation because I'm multiplying the negative times the x. It's a horizontal transformation, which means I'm going to reflect my parent function over the y-axis. And so I end up with a graph that looks like this. Now if I multiply that by 3, it's just going to stretch it out, but my end behavior is going to be the same. And so out here at, out here at negative infinity, this graph is going to infinity. And so just this e to the negative x part, that's going to infinity, and this e to the negative x is also going to infinity. So again, let me rewrite what we've got, what we're left with here. The limit as x goes to negative infinity. So on the top, really what I have is 0 minus infinity. Actually, I shouldn't, this isn't the limit anymore. We're substituting in the negative infinity. This is just what we're left with. Sorry about that. Equal sign. And on the denominator, I have 3 times infinity plus 0. So notice what I'm really left with here is negative infinity in the numerator, 3 times infinity in the denominator. My infinities would cancel out, and I'm left with negative 1/3. And so our answer here, our limit on number 9, is answer D, 1/3.